Hello, I'm Tuukka Korhonen, and I will talk about lower bounds on dynamic programming for maximum weight independent set. So this work considers the maximum weight independent set problem. So in maximum independent set problem, we are given a graph with weights on vertices, and we want to determine the weight of a maximum weight independent set of the graph. So in this graph, for example, these two vertices colored blue form an independent set because there are no edges between them, and they happen to form an independent set with the maximum total weight on the vertices, which is 10. So in this case, we output 10. And specifically, I consider a special way of solving maximum weight independent set, which is by MWS circuits, so maximum weight independent set circuits. So an MWS circuit of a graph G is a circuit that takes as an inputs the vertex weights associated with the maximum weight independent set problem, and then it computes with max and plus operations. So it combines the weights with max and plus operations. And finally, so the weights are some numbers, and finally it outputs some output. And what we want is that for any assignment of weights, of vertex weights to the inputs, we want the circuit to output the weight of a maximum weight independent set of the graph G, for which the circuit is a maximum weight independent set MWS circuit. So here are some examples. So for example, if you have a complete graph, then an MWS circuit of the graph it just amounts to taking the maximum of all vertex weights, because any independent set has just one vertex. And then if you have a graph without any edges, then we can just take always independent set that consists of all vertices. So we can just sum up all the weights. And then the third example, it's a bit more complicated, but what happens here is we just do dynamic programming from the vertex E towards the vertex A. Okay, and yeah, we say that the size of a maximum weight independent set circuit is the number of gates in the circuit. And maybe somebody noticed that these circuits don't actually work if we have a negative input weights, but it's easy to get to do some small transformation to make any circuit that works for positive weights to work also for negative weights. So details like this, they don't matter much in this model. Okay, and yeah, so why do I care about MWS circuits? Is that okay? Maximum weight independent set, it's a fundamental weighted optimization problem, and many algorithms actually for maximum weight independent set and for independent set also, what they actually do is that they implicitly build MWS circuits. So of course the algorithm doesn't explicitly build this circuit, but if we analyze what happens in this algorithm, we find that okay, the algorithm doesn't actually do any decisions based on the weights, but it only does like decisions based on the structure of the graph, and then combines the weights with very simple operations of maximum and plus. So we can actually see that like very well-known algorithms like dynamic programming on tree decompositions, they do this. So some other examples are like dynamic programming on Cordell graphs, and also almost Cordell graphs, and then dynamic programming on click-width expression, and then dynamic programming algorithms based on potential maximum clicks, and the generalizations of this approach. So this has been really popular lately for getting new results for maximum weight independent set, and then of course, branching algorithms. So maybe I claim that within most most of the algorithms published within the last 10 years for maximum width independent set, what they actually do, they just build MWI circuits. So I think this is why it's really interesting to look what really is the power of MWI circuits. So really lower bounds for MWI circuits, they imply lower bounds for of course for all our algorithmic techniques that do build MWI circuits. So this is why I will prove lower bounds for MWI circuits. Okay, now let's go into theorem 1. So for theorem 1, I consider the tree width of graph and the maximum degree of a graph. So the tree width of graph it's a very well-known graph method that basically measures the tree likeness of the graph. So what I prove is that for every graph, I prove a lower bound on sizes of MWI circuits that is exponential in tree width divided by maximum degree. So this lower bound, it holds for every graph G. So it's not like a lower bound over classes of graphs, but it holds for every single graph G. And so this kind of lower bound it's the best possible one can prove in two different senses. So first, what we have is dynamic programming by tree width. It gives MWI circuit of size exponential tree width and linear in the size of the graph, which means that this is basically when we have maximum degree is some constant. This upper bound basically polynomially matches this lower bound given here. So we can say that the dynamic programming by tree width is like a polynomially instance optimal algorithm that builds MWI circuits. So it's like among all algorithms that build MWI circuits, no algorithm can give super polynomial improvement over dynamic programming by tree width on any instance with bounded degree. Okay. And then the second sense in which this theorem is optimal is that basically for any pair of tree width and maximum degree, we have graphs where we have a upper bound that matches this lower bound. So for any pair of tree width and maximum degree. So basically, like this is easy to see, like for like a complete graph that we need to divide by like maximum degree, but it has for every combination of these parameters. So this is really the best possible lower bound you can give with these two parameters. And finally, for theorem 1, one thing I want to notice that what I didn't know myself when I submitted this paper, but from earlier work on DNF compilation, it follows somewhat non-trivially that we have a exponential in tree width lower bound for MWI circuits for constant degree. So basically from this work, this lower bound follows for bounded degree graphs. So basically here the dependency on degree is like really bad. So it's like divided here in the exponent we divide by exponential in D instead of like linear in D. But anyway, so basically when compared to this earlier work, my theorem 1, the novelty here is that we get this dependency on the maximum degree to optimal. So this is yeah. So we give optimal dependency on it. Okay, and then let's go to term 2. So for term 2, we need to introduce some terminology. So we say graph H, it's an induced minor of a graph G. If you can obtain H by deleting vertices and contracting edges of G. it's like graph minors. So graph minors, they are much more well known than induced minors, but here we need to consider. So it's like graph minor, but we do not allow edge deletions. And here we really need to consider induced minors instead of minors because yeah, we really cannot allow edge deletions. And now I define actually a completely new graph parameter, or at least I don't know if this is somewhere in the literature, but I define graph parameter that I call bounded degree induced minor width. So I say that bounded degree induced minor width of a graph G, it's the maximum of tree width H, where H is an induced minor of G with some constant maximum degree. So basically, here is some dependency on the maximum degree. But for our corollaries, it's enough to say that, okay, let's say that the maximum degree is like 3. Yeah. And so what I prove is again a lower bound for MWS circuits. So that is exponential in the bounded degree induced minor width of graph. So again, this lower bound, it holds for every single graph. So every single graph, we have lower bounds for MWS circuits that's exponential in bounded degree induced minor width. And basically, what is the motivation for introducing this graph parameter is basically, okay, we can prove a lower bound on it, but the motivation is that these things become interesting because there are graph classes where this parameter is like linearly equivalent to tree width. So basically, is trivial that in bounded degree graphs we have this parameter is equivalent to tree width because we can just let H to be G. But we also have that this parameter is equivalent to tree width in all planar graphs, and more generally all bounded genus graphs, and even more generally in all graph classes that can be defined by excluding some Fish graph as a minor. So for really large classes of sparse graphs, we have lower bound for MWS circuits that is like exponential in tree width. And therefore, dynamic programming by tree width is again like instance optimal algorithm, like polynomial instance optimal algorithm in all of these graph classes. Okay, and then for term 3, which is the final term I will present here, is we consider MWS formulas. So basically, MWS formula, it's an MWS circuit that is a formula. So whose underlying graph is a tree. So for MWS circuit, we can have like a cycle here, but for MWS formula, the circuit looks like a tree. Okay. And for formulas, I consider instead of tree width, I consider the graph parameter tree depth, which is basically like a tree width, but it has been used for obtaining polynomial space algorithms. So it's like a counterpart of tree width, but for polynomial space algorithms. And this is actually what I think my results give like even more evidence that it's like we have very analogy with this parameter and tree width. And also like also I consider the maximum degree like in term 1. So what I prove is that again for every graph we have a lower bound on MWS formulas that is exponential in tree depth divided by maximum degree. Okay, so this is really analogous to theorem 1. But here, instead of circuits, we have formulas, and instead of tree width, we have tree depth. Okay, and again, we have like matching upper bound, like upper bound that is like exponential tree depth and linear into size of the graph. So we have like again polynomial instance optimality for bounded degree graphs by this construction. And again we have that for every pair of parameters of tree depth and maximum degree, we have some graphs where we have upper bound matching this lower bound. So this is really the best possible lower bound one can give for ambiguous formulas by considering only these two parameters. And here I think there's some interesting difference to the case of ambiguous circuits is that for circuits we have like a efficient algorithm for approximating tree width, but for formulas we don't know of constant factor. I mean, for tree depth, we don't know of constant factor approximation algorithm with time complex like this. So this instance optimality is like non-uniform. So we can construct like optimal ambiguous formulas if we know a good tree depth decomposition, but we don't know actually how to compute good tree depth decompositions. So I think this is interesting, and it further motivates the open problem of finding a good approximation algorithm for tree depth. Okay, now let's go into the proof ideas, or the proof idea of theorem 1, which was the exponential lower bound in tree width divided by maximum degree. So let's make some observation on ambiguous circuits. So let's consider a plus gate with inputs AI and BI that are some gates. And let's say V of AI is the vertices from which there is like a path in the circuit from this vertex to gate AI, and V of BI the vertices from which there is path in the circuit from this vertices to gate BI. And what we observe is that these vertices, they cannot overlap, so they must be disjoint, because otherwise like we would double count some vertex potentially in some solution. And moreover, there must be no edges between these two vertices, because otherwise we would have maybe a solution with some set that is not independent. So basically there must be like a vertex separator for every plus gate. There must be like vertex separator between the inputs of it. Yeah. And now let's to go towards the lower bound. Let's apply some known techniques. So we have what we have is if we have a large tree width on a graph, then there must be some vertex subset, so unbreakable set X, so that any balanced vertex separator of X has size at least linear in tree width. And then what we do is we do this. We use this well-known circuit decomposition technique. There's like a rectangle bound style technique, but like normally this is done like with respect to all inputs, but now we do it only with respect to this set X. So and basically what happens in this technique, we take any ambiguous circuit with tau gates, and we turn it into a circuit of form like AI plus BI from like I is 1 to tau. And we don't really care about like it looks like this, and we don't really care about what happens below here, but we care about so for each AI we have that the intersection of V of AI is with X is at most 2/3 of X, and same also for B. So intersection of each V of BI is with X is at most 2/3 of X. So basically by the previous arguments that okay, each of plus gate it defines some separator, we have that here we have like tau vertex separators like SI like for each of these, and they're like they must be balanced separators of X. So there must be that so these separators SI all must have size like at least linear in tree width. And now we can fool this circuit if there's an independent set that intersects each of these separators SI. The circuit cannot compute a solution corresponding to this independent set. And so basically what we need to show is so the problem is we have like the size of the circuit was tau. So now the problem is given tau vertices like as 1 through as tau, of size at least k, which is a linear in Treevit, can we construct an independent set that intersects all of these vertex subsets? And what I prove is yes, we can. If tau is like a is like at most exponential, is like less than exponential in k divided by 6 times maximum degree of the graph G. And basically, the proof idea here is to use this lopsided Lovász local lemma, which is like a probabilistic tool for showing that there like exists some solutions like in some spaces where we have like a lot of independencies. So basically, how the parameters of this is like we choose each vertex with probability 1 over 2 times maximum degree of G to be in the independent set, and then this shows that okay, we get a independent set, a set that is independent and intersects each of these with some non-zero probability. So this kind of independence must exist. Okay, so this was the proof idea of theorem 1. So basically, the novelty compared to the earlier work is this the use of this lopsided Lovász local lemma to give this optimal bound. And for other proof ideas, so for theorem 2, for the low bound parameters by bound degree induced minor width, basically we again have this unbreakable set in the induced minor, but we then map it to the original graph G, and then use the same decomposition of the circuit, and then we basically have again an application of the Lovász local lemma. But this time it's a bit different, but anyway it works if we have like a constant degree for the induced minor. Okay. And for this lower bound for formulas, we again do like in theorem 1, we extracted like some family of vertex sets, so that hitting all of them with an independent set fools the circuit. So here we do the same. So we again extract these vertex sets from the formula, so that finding an independent set that intersects all of them fools the formula, and use again the same application of the Lovász local lemma as in theorem 1. Okay. And yeah, and finally, so what I think are great directions for future work, or is there are some at least 3 natural directions. So first thing I think is one could prove like similar lower bounds with like max plus or min plus tropical circuits for other graph problems like minimum weight vertex cover or maximum weight matching. And then again, another thing is that we didn't have like a parameterized by tree depth. We didn't have like a lower bound for MWS formulas for like planar graphs. So it would be interesting, like could we give this kind of lower bound also for formulas like we had for circuits? But for me, the most interesting direction of future work is to prove better lower bounds for MWS circuits. So to prove lower bounds for MWS circuits that are more general than what I proved in this work. So some concrete problems would be like what I did. I proved lower bounds that are linear in Treevit for like quite large classes of graphs that are like sparse that all have like bound degeneracy. So one natural question I think is do we have a exponential lower bound in Treevit for all bounded degeneracy graphs? So I don't know if we have or not. Yeah. And then I think another interesting question would be like we have this lower bound parameterized by this graph parameter bounded degree induced minor width. But I think it would be very interesting if we could have some actually upper bound also parameterized by bounded degree induced minor width. So like upper bound of such FPT in bounded degree induced minor width or even XP would be interesting, I think. Okay. Thanks for watching, and if you have any questions or comments, please attend the iClub session or send me email.